Hi everybody, I'm Mark Burgman. I'm at the Centre for Environmental Policy in London at Imperial College, and I'm going to talk today about forecasting and judgment. And firstly, thanks to Eve McDonald-Madden for making this opportunity possible. You'll see a few pictures at the right hand side of the first screen. These are some of the people that have been involved in this research. This is not my research, this is a collaboration between many people, including the fine people on the right hand side and other people in SEBRA, the IDEA team, the Replicats team and others. I'm going to talk about particularly the issue of the origins of thinking about expert judgment and where this might go in the future. My interest or my motivation to be involved in this began with my work for the Centre of Excellence for Biosecurity Risk Assessment back in the early mid-2000s. There are a number of biosecurity risks, disease, pests, pathogens that may enter the country, and we were asked really early on, well, we must follow evidence-based procedures that are consistent with international standards, but often that advice depends upon expert judgment. I'll put this to one side, not too annoying. Expert judgment, and how do we know we have the best possible expert advice? And our answer was, well, we don't know. And we went to ask colleagues in psychology and statistics and philosophy, and there was no clear answer to that question. There was, in fact, very little written, apart from philosophical treatises on informal logic and reasoning, and there's some publications on things like arguments from authority and so on, but really nothing that we could use of a practical nature. So we started to work on this in the context of decision making. Now, decisions, of course, often can be resolved by simply thinking about the problem and thinking about potential solutions systematically. The solutions are often have such small consequences that we don't care whether we're wrong particularly, or in some circumstances the solutions are self-evident, they're obvious. But in many instances in which the outcomes really matter and the data are incomplete, the understanding is incomplete, and yet we still have to make a decision, then we rely on whatever data and understanding we can cobble together, and we rely on expert judgments. And in that small subset of problems in which there are significant consequences and we're really not sure about the mechanics of the problem and the data that will allow us to estimate what we need to know to come up with a certain recommendation, then we rely on expert judgment. So you can of course, as this audience will be well aware, you can reduce a problem in many instances to a performance matrix of N options and M criteria. This is a pretend example. Options for mitigating infectious disease. We have 3 criteria: mortality, cost, and public trust. And we have 3 options: a World Health Organization option, a new option, and a current Australian option, for example. And they imply different levels of mortality, they involve different costs, and will have different impacts on public trust. And we may want to try to apply weights to those things to come up with a decision. This, of course, is abstract and oversimplified. The point is that each of these cells in this table needs to have an estimate. And if we don't have the models and we don't have the data, then we rely on expert judgment to generate those estimates. And our experts make mistakes. We've seen it often enough with things like launching the Challenger space program, providing advice about earthquakes in Italy, making judgments about financial investments, and making judgments about biosecurity risks like the cane toad or foot and mouth disease. Now, all of these things have illuminated the fact that sometimes experts make mistakes. And the question that we were asked early on in the Centre for Biosecurity Risk was, well, how do we know which expert is the right one? So we need experts to estimate simple, verifiable facts, that is, quantities or outcomes that, at least in theory, could be verified externally with independent data. And for example, what's the disease rate in a population? Or what volume of trade do I expect in this commodity next year? We also need experts to predict the outcome of events and to explain the reasoning. Will this pest species enter on this pathway next year, and why? Do you think that may happen? Now, sometimes we ask experts to recommend a best course of action. If we do that, then we necessarily entrain the values and the thinking and the context and the biases of the experts themselves. And if we do that, then we deserve what we get. We shouldn't ask experts for that in particular, because that really is the business of a politician or a decision maker with the responsibility for carrying the consequences or bearing the implications of the consequences if they get the decision wrong. So choosing an expert is difficult. Who counts? Is it qualifications, peer recognition, years of experience? How many experts do you need? How do you know a domain of expertise and whether an expert is within it or not? And how do you ask? How many questions can you ask? How should performance be measured on those questions? How should different opinions be reconciled? And how should reasoning from different analysts be combined, or judgments from different analysts be combined? We've known for a long time, if you note this publication appeared in 1975, we've known for a long time that experts are overconfident. You can see on this slide that there are 7 experts asked 2 questions at a conference way back in the 1970s. And the dashed line represents the correct answer: settlement depth of a clay layer and the height to failure of an earth embankment. And in the left-hand panel, 2 experts enclosed the truth in their intervals, and these intervals represented regions so that they were reasonably sure the truth would be enclosed within them. Only 2 out of 7 in the left-hand panel and none out of 7 in the right-hand panel included the truth. This is a highly repeatable feature of expert judgment. Experts are routinely and heroically overconfident in our judgments about the truth of the matter. We can also see on the left-hand panel that everybody can be biased. All 7 experts in this example on the left-hand panel were estimated numbers that were larger than the truth. We can also see that expert number 4 was quite confident in their judgments in the right-hand panel and quite close to the truth compared to the other experts. Expert 4 was similarly quite confident in their judgment about the truth in the left-hand panel, and they were wildly wrong. So it is, and it is a general finding in this area of research that an expert's confidence in their own judgment is no measure of their accuracy. Now, we've known these things for a long time, and yet the awareness of the frailties of expert judgments has yet to permeate the majority of scientific endeavours. So here, in summary, experts given data use different estimates and methods to calculate these estimates, but in all cases, the right-hand panel, in most cases in the left-hand panel, experts simply didn't enclose the truth. Same experts not always reliable. There's no relationship between confidence and accuracy. And the level of technical skill a person claims to have or has in their CV, for example, does not predict their ability to make good judgments. We'll come back to that later. Experts are affected by the same cognitive biases as everyone else. Here's an example in which Paul Slovic and colleagues sent information about the likelihood that an offender would reoffend within 2 years of being released from custody. At the bottom of half of these, at random, they put a scale that went from 1 to 100. At the bottom of the other half of these pieces of information, they put a scale that went from 1 to 40. If you, a layperson, received the scale that went from 1 to 100, your judgment about the probability of reoffence was roughly 3 or 4 times greater than if you received the same information simply with the scale that went from 1 to 40. The American Academy of Psychiatry and Law was somewhat less susceptible to this same framing bias, but susceptible nevertheless. We did some experiments in which we asked people to make an assessment about how well they thought they would do answering questions that were relevant to our risk analysis in their domain of expertise. These were many different kinds of experts and many different questions. People in the same room on the same day were then asked to assess each of their peers about how well they thought their peers would do on these same questions. And we got a surprising result. The correlation between one's assessment of oneself and the assessment of one's peers has a correlation of about 0.85. The correlations varied from about 0.65 to about 0.9. That is, the way in which we see ourselves in terms of performance on questions of fact are very much like the assessments that our peers make of us. So these are deeply held social beliefs about performance on questions of fact that we and our peers hold. And yet, when we gave the questions to those same people, the correlation between how we believed we would perform and our actual performance was zero. There is no correlation. And this experiment has been repeated by us and by others in many other circumstances. And one's belief or one's peers' beliefs about one's performance on questions of fact, one's ability to make judgments about uncertain quantities or outcomes, is not correlated with what we believe will be the performance of those individuals. This is a rather important thing. It has implications for who we believe to be expert and how they're assessed, because in fact the prediction of performance did correlate with your age and your qualifications and your memberships and your years of experience. So we believe that these things matter, and yet when we come to ask questions that are relevant to a person and their domain of expertise, the sorts of questions that they would routinely be asked to answer when doing a risk analysis, the performance does not correlate with those things. Now, we do know that experts in other domains routinely make errors of judgment about probabilities of future events, and there may be indeed some good reasons for this. If you ask medical professionals to assess the probability that someone has pneumonia, they may well overestimate that risk because they want to be protective. They have a certain attitude towards the uncertainty. Nevertheless, there are some who do make well-calibrated judgments, and they include weather forecasters. We also know that groups do considerably better on a very wide range of tasks than do individuals. This is an estimate of the intelligence of groups of increasing size, from groups of 1, 2, 3, 4, 5, up to groups of size 24. And the group estimate of answers to questions, IQ questions, intelligence quotient questions. As groups get larger, the collective intelligence of that group increases, which is an asymptote, but a group of size about 8 or 9 has a much higher performance on IQ questions than do individuals whose average performance is equal to the population average of about 100. Now, the colleagues that I mentioned at the outset, and I've played a small part in this, my colleagues have developed a set of protocols that allow you to ask for facts that will generate answers that are relatively accurate and well calibrated. And this series of questions: realistically, what do you think the lowest plausible value is? Realistically, what's the highest plausible value? What's your best estimate? And finally, how confident are you that the interval you created from the lowest to the highest captures the true value? If you ask these questions in this order, you will generate estimates from experts that are relatively accurate and relatively well calibrated. If you embed those questions in a protocol in which you draft questions, identify experts, ensure those experts are as diverse as possible, agree on question meaning, make an initial estimate using the questions I've just illustrated, then discuss in a facilitated environment the differences and similarities of opinion, and then get individuals to provide a final confidential estimate of the quantity or the outcome of the event, and then amalgamate those into a single judgment. If you follow that process, you will have a judgment from a group that is relatively accurate and relatively well calibrated, and which will outperform your best regarded expert routinely and by a considerable margin. So if we come back to decision making, which is the core business of this group, when you need expert judgments to fill cells of a decision matrix and you don't have the data to do so in any other way, then this approach will generate in a relatively efficient fashion estimates of quantities that you can use in subsequent decision making. We came to these approaches from our work with primarily the US government, when they asked the same question: how do we know which expert is any good? How do we know who can make good judgments and who can't? Of course, they were particularly interested in geopolitical questions. The idea group, the protocol you've just seen, this histogram shows the outcome of that research. The groups from 5 different universities, university collectives indeed, answered many dozens of questions over many months, and the objective was to improve on the performance of an unweighted linear pool of professional intelligence analysts in the United States. And so unweighted linear pool 1 and 2 on the left and right hand side of this graph were the benchmarks. There were other ways of doing this. There was a prediction market involved, and it did quite well. The idea groups is a second column from the left, and the middle column, the group that won the competition, or the tournament as they call it, was organised by Philip Tetlock and Barbara Mellows and their colleagues, and they used an approach which was not unlike the idea protocol. Get a group of interested people, diverse and interested people, put them together, give them questions, let them make independent initial judgments, and then let them find a consensus position. And our approach is to find a mathematical consensus. The supergroups were a good idea because the group led by Philip Tetlock and Barbara Mellows surveyed 3,000 people, looked for those people who performed the best, put them in a group together, and they did even better. So we just used a vaguely random selection of people. They used a group of people who were purposely selected for their performance on prior questions. And the idea group certainly did outperform an unweighted linear pool, a crowdsourced opinion, if you like, from US intelligence analysts for the same questions. We also learned that some people are much better at this than others. This is our 10 best performers over the period of a couple of years of asking questions. And these top 10 people were remarkably good. Briar scores, the lower the better. I should have mentioned that for the previous slide, but the lower the score, the better. And the people who are the best, 2, 3, 4, 5, 6 people, were surprisingly good over many questions. The black and white circles represent yes and no answers. Occasionally, even the best performing people get things wrong. Very few people no one made no mistakes, but the judgments sometimes were quite wrong, even from the best people. But these people were consistently good and much better than one might expect by chance. We also discovered that if we allow people to see one another's results, ignoring the college students on the right-hand side who weren't particularly focused on doing this well, the Australian and US groups, the open circles represent their initial independent judgments. The closed circles, the black circles, represent their second judgments made after discussing differences of opinion. And if people changed their minds, they tended to move in the direction of the truth. The average Briar score decreased reasonably substantially amongst those people who decided to change their mind. having heard the opinions of their colleagues. This represents some work by Victoria Hemming and her colleagues on the performance of aircraft and the likelihood of aircraft failures. The black circles represent the calibration intervals. We expect people, when they say they are 80% certain that the outcome will be within a particular interval, for that failure to occur 8 times out of 10. And in these figures between round 1 and round 2, the accuracy improved and the calibration improved. And these are the expert judgments of losses of F-16 aircraft per 100,000 hours of flight. These represent the judgments of 23 individuals in 2 different workshops, together with their 90% confidence intervals, and the aggregations of those judgments are in the right-hand panel. And these 5 different estimates represent different ways of aggregating their judgments into a single overall judgment. And in this particular instance, we can see that the round 2 judgments that are generated by giving each person equal weight give very accurate estimates for that particular quantity. I've covered a lot of ground in this short period of time. There's a lot of material behind these, a lot of experiments, which we don't have time to go into. My purpose really is just to introduce you to the idea that there are standardized protocols, structured expert judgment protocols, that will generate estimates of quantities that are in the future, for which we don't have data, for which we need to know an answer to make a decision, and yet we don't have the requisite information available to us. What you should avoid doing is relying on individuals, particularly in circumstances in which logical difficulties or psychological difficulties might arise because of overconfidence, hindsight bias framing, dominance of individuals, and a host of other motivational contextual biases that lead individuals to make estimates and to sincerely believe those estimates and to be substantially biased or wrong. Similarly, to rely on naive groups, unstructured decision, a bunch of guys and girls sitting around a table discussing things, allows dominance and groupthink to emerge. We also should avoid uniformity of context, background, gender, culture, styles of reasoning, and so on. Naive groups are perhaps the worst way of forming a consensus among experts, and yet it is the most prevalent way in which this is done. So what should we do? What does work? If you have individuals, ask questions in different ways, as we did with our question format: lowest, highest, most likely, how sure are you? Ask your experts to consider alternative arguments, counterfactuals, to revise original estimates after they've thought about things, and to anticipate some of the contexts and some of the biases that might arise in their thinking. And then put those individuals into a group. In fact, don't rely on individuals. We know that if you use a group, you will make better estimates of those critical facts that you need to make good decisions. And so discuss questions to eliminate language-based uncertainty. Make your groups diverse. Examine the estimates made by other people during a feedback round, and in doing so, avoid groupthink. These Delphi structures and the anonymity in judgments in the first and second rounds will preclude many of the most pervasive and most debilitating of the psychological and contextual frailties that can lead to poor decisions. I hope this has been a bit helpful. All the best with your decision making in the future, and I look forward to seeing some of your good decisions in the future. I've got a few sort of slides that just to I guess to reinforce the caution with which you should proceed, even in groups. And we have group size going from 1 to 25 in both of these graphs, for example. And here we have different kinds of test questions. And you'll notice that for the most part, as group size increases, performance improves. The average accuracy is on the y-axis, group size is on the x-axis. But for some questions, even amongst standard test questions such as Raven's progressive matrices and heuristics and biases tests, groups can actually amplify the incorrect answer. Even none of this is a panacea. None of this is going to guarantee the right answer. It just means that you are more likely to get an answer that is closer to the truth and better calibrated than if you don't use these tools. Thank you very much.